welcome to another big day in Calculus 1. Today is something that you've been waiting for a long time without even realizing it. Continuity, or more or less connectedness. So you should have, hopefully, somewhere in your life encountered a notion of a function being continuous. We've got this beautiful definition: f is continuous at a if. And I'm about to write something with limits, but before I do, I want you to think back to what did you learn was a continuous function? Somewhere in your past, I'm sure you've heard this word before. What does it mean to be continuous? For most people, chances are what you learned was it's a function that if you draw it, you can draw it without lifting your pen or pencil. So for instance, I'm going to draw some weird curve, and it could do all kinds of weird things. But as long as it's a function, and I can draw it without lifting my pencil, then that is continuous. But if I can't, and there's a number of ways this could happen, so whoop, something with like a jump, or a hole, or even an asymptote, and maybe this hole even has like another dot up here. All those places where I can't actually draw that function without lifting my pen, that is probably what you learned is not continuous. Oops. Now, that makes some pretty good intuitive sense. It's usually where I like to start, and it's a really important idea for a couple reasons we'll talk about in a minute. But I want to get a little mathy on this because I like to appreciate what we're learning. If that was your definition of continuous and you said, I got to make this formal, because clearly that's not super clear. If I had to prove something wasn't continuous, it's not clear what I would need to show. Like, no, nobody could draw this without a pen. You hope someone agrees with you. You hope that you could draw the function reasonably. So how could you possibly give a real mathy definition for that? And this is not obvious at all. This took quite a while to come around to. And even the way we write it now is a lot simpler than how it was originally written. So here's where limits are going to save us. So a function f is continuous at a if the limit as x goes to a of f of x equals, you ready for this? It's the simplest thing you could ever possibly want. It's a gift. So f of a. In other words, it's continuous if I'm allowed to just plug in. If I can take that a and just plug it into my function. That's our definition. It's kind of one of the reasons why we have this definition of limit. So continuous just means you're allowed to plug in into a limit. If you couldn't plug in, well then something else is going wrong here. And when you look at this example to the right, all these places where it's not continuous, that's either where the limit doesn't exist or where taking that limit isn't the same thing as what the function says it should be. And here's our fun note. Continuous, to be continuous, well, here's our definition, but it also implies two things. It implies, that's what this arrow means, implies a is in the domain. So if it's not in the domain, I couldn't plug it in here. So an asymptote is usually a case where a is not in the domain. Some holes. It also is telling you that the limit exists, because otherwise this left side wouldn't be here. So this doesn't make any sense if the limit doesn't exist or if you're not in the domain. Okay, I hope you realize that is kind of a clever way of defining continuity. It's pretty neat. Usually at this point, what people really got to do is see a bunch of examples and then go back and realize, oh yeah, that is a clever way of saying this. And then at the end, we'll also talk about why the idea of continuous is the right idea to focus on in a lot of cases. Why is this the right property that helps us do things other than take limits fast? So here's another note. When it's not continuous, we'll usually say it is discontinuous or it has a discontinuity at a. So if I use those words, it just means not continuous. All right, I like to start with graphs. I think most people think best with graphs. So here is a function. And you might even think to yourself, how could I draw this? Where can I draw without lifting my pen? We want to know where is the function continuous? That's everywhere where I don't have to lift my pen. But you also might think, hey, where could I take a limit, and where can I find the function value, and where do those agree? And so in this case, it looks like everything is fine starting at 1, but not including 1. And everything is fine until I get to this first hole. And then my function is not even defined there. And so this is going to be at, so from 1, not including 1, so it's an open bracket, to 3, not including 3. Okay, and I'm going to do my little union sign here. Then everything is fine from 3 until I get to 6. And here my limit doesn't even exist. My function exists, my function value is 3, but there's a jump there, and so that is going to be at a, looks like it's, so from 3 to 6. Notice I've got these open parentheses, so this does not include 3. At this point, you might want to go ahead, go back. At this point, you might want to go ahead and say, hey, can I finish this list now that I see what he's going after? Take a second. If you're with a friend, tell a friend. Okay. Oh my gosh. Sorry about that. All right. So we are going to take a union and say from 6, we are good until we get to 8. From 8, we are good until we get to, oh, I lost my union. Lost my union again. We're good until we get to 10. From 10, we're good until 13. Oh no, I've got to wrap around. Union from 13. We are good until we get to, now here's a question. This point here, so we crossed this asymptote, and that was bad. We weren't in, that's definitely not continuous there. This corner here, you might ask yourself, is that okay? And if I ask myself, what is the limit? Well, the limit is just going to be the tip of that corner. And the function value is the tip of that corner. So this is fine. And then it looks like this is going off to infinity. Great. Pretty ugly. So I don't really have a really great way to write this any other way. You could list the discontinuities. So we could go the other way and say, oh yeah, it's not continuous when we're less than 1 and when we're not at 3. So that'd be another way we could write this if you really want to. I'm not too picky as long as it is true the way you're writing it and it is precise. Okay, so saying the opposite, where is it discontinuous? It is discontinuous at, we are probably not going to bother writing 1 because that is the edge of the domain. So this function's domain, right, any reasonable mathematician would say, oh yeah, don't bother writing this because that's not really even a part of the function. So it is discontinuous, however, at 3, 6, 8, 10, and 13. Okay, great. And a lot of times that's how we'll write it, or we'll write this is continuous when x is not those. So hopefully that makes sense. Graphs are important, both that you can read them and that you can communicate through them. If anything, part of the point of pre-calculus is to make sure that you're comfortable with the algebra and the function notation and the graphs. And so I'm going to continue to reinforce all of these different ways of writing and thinking about things because everyone is important and they help each other. Okay, I'm super excited about this next part because I've been using these words for quite a while and we haven't really properly defined them. But there are 3 types of discontinuity, and I hope that these come quick because I've said them so many times. So there's 3 types of discontinuity and you've seen them all, and this is it. There aren't any other ways for a function in one variable to be discontinuous. It either has a hole, a jump, or it's an infinite discontinuity. So let's give an example of each of these, and maybe you can find them in the graph above as well. So here is a quick example of a hole. How about x squared minus 1 over x minus 1. This thing, if you graph it, has a hole at x equals 1. Why is that a hole? Well, if we simplify this, this actually simplifies to x minus 1 times x plus 1 over x minus 1. Those two things cancel, so this is just equal to x plus 1 as long as x is not equal to 1. Right. And so at that 1, we get a shape that looks a little bit like that. Just one single point. It looks like x plus 1 except for that one little hole. And maybe you can find an example of that up in that graph. In fact, there's two examples, believe it or not. One of them, the function is undefined. The other one, the function is defined, but it's defined to be something different. Okay, so a hole, being a little bit more precise here, this is the case when the limit exists. But does not agree with my function value. Okay, so the limit here wants to fill that hole. That's great, but the function says, no, I'm not defined there. So there's a disagreement between the limit and the function, and that's what it means to be a hole. And we see that here too. The limit and the function value, here there is a function value, but it doesn't agree with the limit. And so if those two disagree, that's called a hole. Okay, next up, a jump. A jump, we've seen a great example of this already. So this is, we've seen more than one example. Let's do this one. Absolute value of x over x. And we saw that this looks a little bit like this. So there's a jump, and I've used that word before. So you could probably find, it looks like two places where there is a jump in the graphs above. One right here and one right here. What is the actual definition of a jump discontinuity? Well, this is the case if the left and right limit are finite, so no asymptotes, but don't agree. Okay, and so that's what we see here, that there is a left limit. In this case right here, it looks like the left limit is a 3 and the right limit is a 4, and those do not agree, but they are both finite. And so it would take a jump. You've got a leap from the lower one to the upper one, and here from the upper one to the lower one. So luckily for us, these words are describing what they really are. Okay, last one. Maybe you can guess what this one is. Infinite. So we have many examples of this, but let's just do the easiest one. How about 1 over x? Okay. And the point here is that this has a discontinuity where either the left or the right side go off to infinity. And so this is going to be the case if we have a vertical asymptote. Literally the same thing. Okay, so you have it. It is an infinite discontinuity if you have a vertical asymptote. In fact, I would forgive you if you just called it a vertical asymptote. I don't think that's a very meaningful distinction. But you can see that there is one such case here. I would say one, which is right here at 13. Normally, we wouldn't bother to say 1 because it's the edge of my domain. I don't plan on being super picky about that, but maybe your homework will be. Okay, so what is the definition here? Well, let's think about this a little bit too. We said on one case, all right, if the limit exists, but it doesn't agree with f, then that's a hole. We said, okay, if the left and right limits don't agree, in which case the limit doesn't exist, then that is a jump. And finally, we say that is infinite if, well, what is left? What is left? Then we're going to say if the left or right limit either one, doesn't matter, maybe both, is plus or minus infinity. Okay, so those are the three types that you're going to see. We could, if we wanted to, get a little weird about this and bring up things like that sine of 1 over x, where that limit doesn't exist. And then I would have to get a little bit more technical on which one of these I should go into, but let's not worry about that right now. If you're really interested, ask me later. Okay, great, that's it. That should be really reassuring that these are the three things that can go wrong. So if you know how to spot these three things, then you should be able to tell when a function is discontinuous. Okay, so let's do a couple of quick examples here. I haven't even really shown you how to do it, but I bet you could figure this out. Take a minute, give these a shot. I'm gonna hope you just took a minute. Pausing is great. Where are these functions continuous? So, in these first two cases, I hope you know what these kinds of functions are called. They have a polynomial on top and a polynomial on bottom. So that is called a rational function. It is a ratio of two polynomials. Now, we had a result last time that told us how to find the limit of a rational function. And it said, just plug in all but one case. Okay, so we can just plug in to find these in all but one case, and that one case is if the denominator is 0. So all we're really asking is, this is going to be continuous. Ooh. When the denominator is not equal to 0. All right, so where is this denominator 0, or when is it not 0? Well, that's going to happen exactly when x plus 4 does not equal 0. I can solve that. I'm really good at precalculus. Boom. Great, so this is continuous everywhere except for -4, and in this case, if we went a step further, we could actually show that this is going to have an infinite discontinuity. Here's how I know. If I plug in -4, okay, if I plug in -4, then the top is going to go to, looks like 16 minus 4 is, oh man, I totally screwed this up. Okay, so this in particular is going to have a hole, and I'm going to leave it to you to figure out why it's a hole, and I'll even give you a hint. You should try to factor the top and see if you can cancel something out. This next one, again, we're going to say where is the denominator 0, and that's going to be when is it not 0? That's when x squared is not 0, and that's going to happen exactly when x is not equal to 0. Okay, so this one is going to actually be infinite. And maybe I'll go back and label that first one too. This one's going to be a hole. Okay, the big difference here, if you're keeping track, is that if I was going to try to plug in -4 up here, you would actually get 0 over 0, which is telling you to do some work. If I plugged in -4 over here, I would get 1 over 1 over 0. And so this 1 is going to stay a 1, and as the bottom gets smaller and smaller and smaller, this whole thing is going to blow up and go off to infinity. Okay, in the first case, you can actually cancel out that x plus 4 with a factor of the top to see what you should get. Great, so those rational functions are definitely our friends. Let's go ahead and look at these two, and we're going to do these fairly quick here. So this piecewise function, it's definitely going to be continuous when it is 0 here. So it's definitely continuous when x is less than 0. And it's definitely continuous when x is greater than 0, because then I'm strictly in this bottom one. The question here is, what happens when I am right at this border here? And I hope you can tell that the limit from the left is a 0, the limit from the right is a 1, but the left and the right don't agree. So this is just going to be x not equal to 0. And we could check that by graphing it. You should get something that looks a little bit like this for your graph. Okay, the power of sketching really helps out. So this is not continuous at 0, and furthermore, what kind of discontinuity is it? It's going to be a jump discontinuity. So I'm going quick. It is worth practicing. Hey, can I write this out using the correct notation, saying a limit as x goes to 0 from the left and a limit as x goes to 0 from the right, and see if you can fill in those two to see that the limit actually doesn't exist, and so it can't be continuous. All right, number 4, j of t. I wanted to do this one. It is also not going to be, this is going to be continuous everywhere except for at 0, but maybe for a different reason. If I was going to graph this out, then what happens is it is 1 everywhere except for at 0. That's what this says. But at 0, I get some crazy high value, which is a 7. Okay, so this is also going to be a hole. Maybe I should label this one also. This is a jump. Okay, so good to see these things in an algebraic fashion as well. All right, do take some time, make sure each of these makes sense to you, and that you could, in theory, explain it to someone else.